going to switch our attention now to start focusing on planes in 3 space. So we've seen that a line is determined by 2 things. That could be 2 points, or that could be a point and a direction. Well, similarly, a plane in 3 space is going to be determined by 3 things. One possibility is that it's determined by 3 points. If I have 3 points, that's going to uniquely determine a plane. To illustrate that, let's just suppose I've got a point and a point, so I just have 2 points. Well, there are infinitely many planes that contain those 2 points. Those 2 points would determine this line. Now, clearly that line is contained in the plane consisting of my whiteboard, but that line is also contained in this plane, and this plane, and this plane, and this plane. So there are infinitely many planes that contain those 2 points. But as soon as I draw a 3rd point, so now I've got this point, and I don't know where the other one went, we'll say that one, and this one, the whiteboard here is the only plane that contains those points. Because if I were to come forward to be in front of the whiteboard or backward to be behind it, I'd have to curve, and planes don't curve. So 3 points will determine a plane. Okay. I can also determine a plane by 1 point and 2 vectors that are parallel to the plane, but not to each other. So they're essentially giving me 2 different non-parallel directions. Let's just take a look at how that works. If I use these markers to be my 2 direction vectors, I can pretty much see that once I have these 2 directions, I can put a plane down. That determines the directions in which my plane needs to be. But I can put this at a different location. So this determines, essentially, I'm going to have planes parallel to this one, but then I can put it wherever I want. Well, that's what the 1 point does. That tells me where to put that plane. Now what we're going to do is we're going to take advantage of the fact that we can characterize a plane using these 3 things. Because what I'm going to do is I'm going to consolidate all of the information contained in these 2 vectors that are parallel to the plane into just 1 piece of information. So that a plane, just like a line, as long as we're in 3 space, that plane can be determined by just 2 pieces of information. So the idea is that when I have 2 vectors that are parallel to the plane, and let me just remind you, parallel to the plane means visually exactly what you think it would. This is not parallel to the plane, this is. If a vector is parallel to the plane, when I put its tail on the plane, the tip is on the plane too. So if I translate it so that the tail is on the plane, the tip will be as well. Okay. Now, if I have 2 vectors that are parallel to a plane and I'm in 3 space, okay, then these 2 vectors determine a semi-unique, what we call normal direction. When we're talking about vectors and planes, rather than using the word perpendicular, we use the word normal. But if I have these 2 vectors here that are parallel to my plane, then the normal direction would be either this direction or its opposite. Those are the 2 directions that would be perpendicular to both of these vectors. Okay? And obviously I could scale this so the magnitude of this vector could be anything non-zero, but it's a semi-unique direction, this direction and its opposite. And so I can consolidate the information about 2 vectors that are parallel to the plane by giving 1 vector that is normal to the plane. So with that, that should give me enough information to uniquely determine a plane. Let's just try that out visually. Let's suppose this is my point, and this is my normal vector. So I want a plane that's right here where I put my fist, and I want this vector to be normal to the plane. Well, it's going to have to be this plane right here. Okay. So how would I go about then getting an equation for such a plane? Well, let's take a look at an example. Let's suppose I have the point P, 2, negative 3, 4. Okay. And let's suppose that my normal vector, which I'll call n for normal, is 2, 5, negative 1. And I would like to come up with an equation for that plane. Well, just to illustrate this, let's suppose that that plane is this whiteboard right here, so that the normal vector n is coming straight out. Okay, so I've got this point P here, 2, negative 3, 4. I want the equation for my plane to describe an arbitrary point Q, which I would label with variables, x, y, z. If I've got an equation for a plane, if I plug in a point on the plane to that equation, it makes the equation true. If I plug in a point not on the plane to that equation, it makes the equation false. So this Q here, even though I've written it in terms of variables, I'm meaning it to mean a point on this plane. So this point out here, not on the plane, it's not called Q. I can't describe this as x, y, z. Now what I can do is I can form this vector PQ. Now I know how to do that. We just subtract components, remembering that we subtract from our ending point minus our starting point. So this would become x minus 2, y minus negative 3 would become y plus 3, z minus 4. Now what do I know about this vector? Well, what I know is I just drew it with its tail on the plane and its tip on the plane. It's a vector that's connecting 2 points on the plane. It is parallel to the plane. But if it's parallel to the plane, what's its relationship to the plane's normal? The relationship to the plane's normal is that it's orthogonal. Notice I said orthogonal, not perpendicular. That's actually very important because this point right here is on the plane. So if Q is an arbitrary point on the plane, it's entirely possible that Q could be the same point as P, in which case PQ would be the zero vector. Now the zero vector is not going to be perpendicular to this normal vector, but it will be orthogonal to it. And what does it mean for vectors to be orthogonal? It means that their dot product is 0. So I can say I know that n dotted with PQ has to equal 0. That's got to be true if Q is a point on the plane. If Q is not a point on the plane, well then my vector is going to have some, in this case, outward or inward direction. It's not going to be the zero vector, and it's not going to be perpendicular to this vector. So this equation will be false if Q is not on the plane, true if Q is on the plane. So that gives me my equation for the plane. Now I'm not going to leave it in this vector form. Let's actually write out what that gives us. So n, we said, was 2, 5, negative 1. PQ was x minus 2, y plus 3, z minus 4. And I need that to equal 0. When you're writing an equation for a plane, I will usually ask that you simplify one step beyond this. Get to the point where you don't actually have any vectors in your equation. So just do the dot product. That's going to be 2 times x minus 2 plus 5 times y plus 3 minus the quantity z minus 4 is equal to 0. That is an equation for the plane. That's in what we call point normal form. So in general, if I have a point x naught, y naught, z naught, and a normal vector a, b, c, point normal form, I like to actually sort of think through the process rather than just memorize the result. So I always let Q be an arbitrary point on the plane. That way, PQ is going to be a vector that's parallel to the plane. So point normal form just says n dotted with PQ will have to equal 0. Now, if I work that out, that's going to be A, B, C, dotted with x minus x naught, y minus y naught, z minus z naught is equal to 0. Now I can simplify that a little bit further if I like. In fact, I would ask you to. Don't leave it with vectors in it. So that's going to give me A times x minus x naught plus B times y minus y naught plus C times z minus z naught is equal to 0. Totally fine for you to stop at this point, which is point normal form. Now, if I want to, I could simplify things a little bit further. Okay. So I could distribute the a's, and I could say this is ax minus ax naught, plus distribute the b, by minus by naught, plus distribute the c, cz minus cz naught is equal to 0. Now, if I look at this, ax, by, and cz, those are the terms that contain my variables. All of these other terms are just constants. A, B, and C were constants. They were the components of my normal vector. X naught, Y naught, and Z naught were the coordinates of the point that I started with. So if I want to, I can consolidate them, and I could write this as AX plus BY, plus CZ plus D is equal to 0, where D would just be the sum of negative AX naught minus BY naught minus CZ naught, just the sum of all of those constants. This is what we call standard form, and you'll often see a slight variation on it. Very often that constant would be subtracted over to the other side. So you'll have some x's plus some y's plus some z's equal a number, or some x's plus some y's plus some z's plus a number equals 0. Either of those is pretty much considered standard form, okay? Although obviously if I subtract this number over, it's going to be different. So I shouldn't say either one is standard form. This is standard form, but often you'll see a slight variation that number is subtracted over, okay? One thing that's nice to notice is that the coefficients in front of x, y, and z tell me what the normal vector is. So if I'm finding an equation for a plane, I'm almost always going to put it into point normal form. If I'm given an equation for a plane, it's usually given to me in standard form or some slight variation on that, but I can pick out just from looking at the equation a vector that would be normal to that plane.